Okay, in this video I'm going to talk about the logarithmic derivative. So, in mathematical analysis we have like regular derivative, which is like denoted. So if we have a function f, then the derivative is denoted by either df divided by dx, so f of x, let's say. Or it's also denoted as f prime. So for a logarithmic derivative, like the logarithmic derivative by definition is just the f prime of x over f of x. So this is the logarithmic derivative. Yeah, so there is no like a standard notation for it. So I will use the notation LD of x, not of x, but of f. Yeah, so LD of f, this would be a function of the argument x. So let's write this more carefully. LD of f, and this is a function of the argument x. Yeah, so, but this is not a standard notation, like there is no, it seems that there is no standard notation. So, like why would we need this, and why is it useful, and why is it called logarithmic derivative? What's logarithmic about it? So so first we notice that the product rule can be rewritten in the following way. So so the ordinary product rule for differentiation is that if we have functions f and g, then the derivative of the product is equal to f prime g plus f g prime. So let's divide it by let's find the similar product rule for the logarithmic derivative. So we need to divide both, so we need to find fg prime over fg, right? So this would be the logarithmic derivative of fg, logarithmic derivative of fg, and this in turn, so we keep the denominator, and in the numerator by the product rule we get f prime g plus f g prime, and now this would be equal to f prime g over fg plus fg prime over fg. Now g and g cancel each other, and f cancel each other, so we have f prime over f plus g prime over g, and this is exactly, so f prime over f, this is exactly the logarithmic derivative of f, and f prime g prime over g is exactly the logarithmic derivative of g. So this one, so plus logarithmic derivative of g, right? So we see that the logarithmic derivative of the product fg is equal to the sum of the logarithmic derivatives of f and g. So this product rule in this case is much simpler than the product rule for the regular derivative. So that is one of the reasons why it's convenient to consider this, and also it indicates why it's logarithmic, because for like this formula it's very much similar to the one of the properties of the logarithms. So like we have logarithm of the product with some base a, like of the product xy of the numbers x and y, so is equal to the sum of the logarithms, logarithm of a plus the logarithm of x plus the logarithm of y. So the logarithm of a product of two numbers is equal to the sum of the logarithms of these numbers. So this similarity with this product rule. So let's write the product rule here separately. LD of fg is equal to LD of f plus LD of g. Yeah, so that's one reason, and actually there is another reason. So the logarithmic derivative, it actually can be expressed as like in terms of the actual logarithm. So if we because if we consider the derivative of the function natural logarithm of f of x, right? So this function, and consider the derivative of this, right? So then what we get is, so by the chain rule, we get first the derivative of the logarithm, and derivative of the logarithm is 1 over f of x, right? Multiplied by the derivative of the argument of the f of x, so multiplied by f prime of x. So this is exactly, yeah, so this is exactly the logarithmic derivative of f. Right, so logarithmic derivative, it's actually equal to the derivative of the natural logarithm of the function. So so that is a second reason why it's called logarithmic, why it makes sense to call it logarithmic. Okay, so so now so why, like where we can apply this? So because of this product rule, which is much simpler than for the regular derivative, we can apply, like we can find, like we can use it to find derivatives of some complex products. So let's say that we have a function that is a product. So let's say that f of x is just an example, like let's say x to the power of 4 multiplied by x minus 2 squared multiplied by x minus 3, something like this. Like it can be more complex, but like let's do just for this. And so let's say that we have a problem of finding the derivative of this, right? So we could in theory just apply the product rule, like the regular product rule, this one. So like we have a product of three functions here, so we apply the product rule, and like it would be a giant expression, and eventually we would find the derivative. But but using the logarithmic derivative actually simplifies the calculation here. So let's find, so instead of finding the derivative of f, let's find the logarithmic derivative of x, and then we will express it. Then we will express the derivative in terms of logarithmic derivative. It's not difficult, right? So logarithmic derivative not of x but of f. So logarithmic derivative of f would be equal to the sum of the logarithmic derivatives of x to the power 4 of these three functions, right? So plus, because again the logarithmic derivative of product is the sum of logarithmic derivatives, so that's why the product becomes a sum. The product in the argument becomes the sum of the logarithmic derivative. So plus the logarithmic derivative of x minus 2 squared plus the logarithmic derivative of x minus 3. So then each of them, so the logarithmic derivative of x to the power 4, so this would be 4x to the power 3, right, over x to the power 4. So this is by definition. Then plus 2x minus 2 over x minus 2 squared plus 1. So again, in the numerator I write the derivative of the function, and in the denominator I write the function itself. So this is simplified to 4 over x plus 2 over x minus 2 plus 1 over x minus 3, right? So and then so this is the logarithmic derivative of n, and then the regular derivative is equal to f multiplied by the logarithmic derivative of f. So this would be equal to this function x to the power of 4 x minus 2 squared x minus 3 multiplied by this sum that we calculated, 4 over x plus 2 over x minus 2 plus 1 over x minus 3, and that's it. So this is the answer. So this expression is the regular derivative. So the regular derivative of f is this function. So you see that it's much easier to calculate this than if we would apply the product rule directly. If we apply the product rule to this three function directly, like the calculation would be much much greater. Yeah, so that's one of the applications. Yeah, so that's it for this video.